Hello everyone, my name is Hubert, and today I'm going to give a talk about hydrodynamic design of the humpback whale flipper. And first, let me introduce the humpback whale. The humpback whale is a species of baleen whale. It is one of the largest whales, with adults ranging in 12 to 16 meters and 25 to 30 tons in weight. And also, it is known for breaching and other service behaviors such as bubble net feeding. And this is breaching. Breaching is a leap out of water to communicate with other whales who may be far away. And this one is called bubble net feeding, and unique feeding method for humpback whale. But today we only discuss the humpback whale flipper. Humpback whale flipper has longest flipper of any cetacean, and its flipper length is 0.25 to 0.33 of the total body length. And also the flipper is symmetrical, streamlined profile, and tubercles located on the leading edge. These features will be mentioned later. This is tubercle. At the end of the study, first we want to characterize the design of the humpback whale flipper. And second, we want to compare with the well-designed hydrofoils or airfoils and find out whether they are similar or not. Coming to materials and methods. And the sample we used in the study is a dead whale from Island Beach State Park in New Jersey. The left pectoral flipper was removed from a 9-meter male humpback whale. And the flipper span was 2.5 meters as measured from the distal tip to the anterior insertion. Then the flipper was cut into 3 approximately equal segments, which is distal, medial, and proximal. And the distal and medial segment was cut into 2.5 centimeter cross section. And cross sections were numbered sequentially starting from the flipper tip. And a total of 71 cross-section was cut from the distal and medial flipper segment, with section 8 and section 22 lost. After that, each cross-section was photographed with this camera, and flipper section was measured using a GTC or digitizer interface to PC. Let's talk about the results. The flipper is 28% of the total length of the whale. And there's a slight sweepback of 90 degrees on the distal third of the flipper, about this one. And the aspect ratio was 6.1. And aspect ratio is flipper span squared divided by flipper area. The flipper has a large rounded leading edge and a thin tapering trailing edge. And bones were present in both anterior and median portion of the section. And the cross section was symmetrical about the proximal core to section 10. And distal tip section were scooped out along the ventral leading edge, producing a concavity. This. And the mean thickness ratio for the cross section was 0.23. And thickness ratio is maximum thickness divided by core length. And looking at the graph, x-axis is the section number and the y-axis is the thickness ratio. And thickness ratio range from 0.28 at section 2 to 0.2 at section 37. The position of maximum thickness decreased steadily from a maximum of 0.49 at the flipper tip to a minimum of 0.19 at the mid-end. Coming to discussion, the effectiveness of humpback whale flippers as hydrofoils, this is hydrofoils, and for wings is determined by the hydrodynamic design, which influences lift and drag characteristics. An effective hydrofoil produces a large lift while minimizing drag. And lift is generated when it is cant at an angle of attack. The angle of attack is an angle between the body reference line to the oncoming flow. And the lift is a component of the force that is perpendicular to the oncoming flow. And drag is the opposite force resisting the moving object. And once above the critical angle of attack, the hydrofoil stalls, which will lose lift. The symmetrical cross-sectional designs of the flipper generates lift and minimize drag. And the elliptical flipper provides the optimal shape for uniform distribution of lift over span and incurring the drag. Flip cross-section has a streamlined design similar to engineered high-performance hydrofoils and hydrofoils. And this is the shape of the hydrofoils. The magnitudes of lift and drag on the flipper are also influenced by the maximum thickness, by the position of the maximum thickness, which is similar to the normal foil design. And maximum thickness of the flipper is determined by bones, which provide strength against transfer loading to the leading edge and medial portion of the flipper. And high AR wings are favored for sharp, high-speed banking turns because of their high lift characteristics. And the lift force developed by the wings has a horizontal component that supplies the centripetal force necessary to maintain the turn. In addition to AR, sweepback and taper can improve lift generation and drag reduction. However, the sweepback taper wing carry more lift near the tip, which stall at a distal wing, and which leading to instability in roll. So in aircraft design, this problem is solved by installing washout, and this is washout at the tip, wing tip, which decrease the local angle of the wing and the tip, so lift is spread elliptically over the entire wing. And there's a similar function is the ventral concavity. Displaying the distal of the flipper. This will provide a wire with sufficient lift and stability at a high angles of attack required in maneuvering. And the tubicles may function to generate vortex by unsteady flow to maintain lift and prevent stall at high angles of attack. And we also found that the function of the tubicles may be similar to strake, this one on the airplane. And stalling is postponed because the vortex exchanges momentum within a boundary layer to keep it attached over the wing surface. Now look at the graph on the left. The good red on the left indicates the good performance of the flipper. The foil on the bottom one has a similar design to a flipper, and others vary from thickness ratio. As you can see, this one shows that the better thickness ratio can maintain the lift force and postpone stalling at high angle of attack. Now finally, we have characterized the design of the humpback whale flipper, such as high aspect ratio and good performance of position of maximum thickness and thickness ratio. And also we have compared with the we found humpback whale flipper similar to well-designed hydrofoils and aerofoils. Thank you for listening.
I want to know, do these special flippers bring any benefits for humpback whale themselves?
I want to know the special flipper brings benefit to the whale. And such as bottleneck feeding, I mentioned before. They need to it requires a high mobility for whales to do this feeding method. We mentioned that this like the AR was very high, means the flipper was very long, and some sweet back and a good thickness ratio are of both benefit to the whale.
I want to know, where do you get your material?
Oh, we get material. You want to know where do we get material? To get this material from the New Jersey, in the Island Beach State Park in New Jersey.
I want to know why you choose this place to get your material.
Oh, you want to know why we choose this place to get materials? And in this paper, it didn't mention this.
In the discussion, conclusion. Sorry. The right picture, I want to, can you explain again?
Can you repeat the question?
Last picture. Yes. I want to know the right picture because the axis is too small. And can you explain again this picture?
This picture?
Yes.
I want to know what is this picture. And this is thickness ratio of the humpback whale. And we designed a foil which is similar to this humpback whale to show the humpback whale can maintain lift and prevent stall at a high angle of attack. So.
Did you explain the right figure?
I think I can. Right figure is the thickness ratio here, and the axis is the section number, which is from the flipper distal tip to the interior section.
the function of the tubercles on the humpback whale?
So we want to know the function of tubercle for humpback whale. So since the humpback whale need to do some high maneuvering, so it requires high stability, and tubercles can help the humpback whale to maintain lift and prevent stall as this aircraft.
This is actually a very interesting topic. However, it requires some presentation skills to make it understandable. Right now, it's still relatively not understandable. This is because you haven't used enough image. You need to, when I was reading your paper, my first thought was, oh, this guy must have to use a lot of image in order to make himself understandable. Okay, so for example, here in your results and discussion, you have a lot of terms. All right, that's fine. And for example, when you talk about, thickness ratio, for example, here you just describe it. TR, okay, TR means thickness ratio. Thickness ratio means this equation. However, this didn't give us a concrete image of which we have a flipper. It's an object. Apparently, the scientists, they did some measurement of this flipper. Where did they measure? What do they measure to obtain this ratio? It would be easy if you can just draw a simple graph and say, they measure this and that to get this ratio. That's the first thing. You have to really make it, for everything you talk about, you need to give an image. Okay, and also for aspect ratio and many other things like P and T or whatever. Yeah. Okay, that's the first thing. Second is, you have this section number. It's also nice if you can either show this next to this, or you tell us this is proximal, this is distal. However, proximal and distal are difficult terms, again, for the class. So it would be great if you just show this, all right? Okay, because you already have a lot of terms, okay? And then the next thing is here, for example, I remember one word. You say the aspect ratio is high. Where is the graph of aspect ratio? Do you have a graph of aspect ratio? Data? Where is that? Where is your aspect ratio? No? A value? Where is the slide of aspect ratio? Show me. AR, you have a value of AR, or where is the aspect ratio? All right, he said something like the AR is high, is that right? Okay, however, how do I know which value means high? You say this guy is 180 centimeters, he is tall. How do you know he is tall? Because on average, most people is only 160 to 170, and he is 180. So you say something is high by comparison. That's something you have to keep in mind. So you really need to give us a level for comparison to know that. Okay, and there are so many places which I will tell you, you need to give us image to explain you better. And I will list them under your video, okay? And then it's nice, I appreciate that you explain. And you explain when you compare the flipper with the other hydrofoil, you look for images. However, still, even if you show images, still it doesn't really explain well. Because, for example, you say ventral cavity, and you show this. I was really wondering, what do you mean by ventral concavity by showing this? So that means you didn't choose the right image to explain yourself. So you have to choose a better image. Okay, there are so many terms. Okay. All right. So and finally, coming back to Fiona's question, she asked, "What's the benefit of this whale's flipper to them?" Then please next time try to include this, because at the beginning you are talking about their swimming behavior like this and that. Next time please come back to this by saying because of this morphology of their flipper, they are able to do this. So you will give you better coherence next time. Okay, thank you, Hubert.